Hello everyone. Today we will be concluding our discussion of traveling salesman problems with one more algorithm for solving them, and that is the cheapest link algorithm. Like the nearest neighbor algorithm that we introduced in the last video, the cheapest link algorithm is also an approximate algorithm, meaning that it doesn't give a perfectly optimal solution every time, but it's definitely very fast and efficient as compared to the brute force algorithm where we have to solve every single possible option. So the nearest neighbor algorithm, the cheapest link algorithm relies on selecting the edge with the lowest weight in the entire graph first to be part of our circuit, or tour, I should say. And then we go with the next cheapest one in the whole graph and so forth and so on until we've got a circuit that visits all of the vertices exactly once and includes all of the vertices, of course. Now, there's a couple of things we want to avoid when we're doing this. We want to avoid picking edges that result in a third edge going to one vertex, and we want to avoid edges that result in a partial circuit, meaning a circuit that includes not all of the vertices in the graph. So, looking at our example here, if we look at this graph, the cheapest edge that we see, or edge with the lowest weight on the whole graph, is this one from B to E with a weight of 7. So we are going to pick this one first and add it to our little graph that we're filling in over here. Next, we have a tie between two edges that have weights of 8. So from D to E is one, and then from D to A is the other. Fortunately, we can actually add both of these edges without creating either a closed circuit that does not include all of the vertices or having a third edge going to one. So we'll add both of those. And then at this point, the next cheapest one on the graph is from A to C with a weight of 9. So we'll add that. And then the next cheapest ones are from C to E and from A to B. Both of those, if we added them, would put a third edge going to either E or to A, so we don't want to use those. Next cheapest one at 11, D to C, but that would make a third edge going to D, so we don't want to do that. Also, say we were to add that, that would also create a partial circuit between A, C, and D, and then back to A, so we've got like a closed loop that does not include all of our vertices. We don't want that either. So our next best option is going to be going from C to B with a weight of 12. Now, at this point, we're going to add up the weights of all of the different vertices in this. So we are going from A to D to E to B to C and then back to A. So our total of all our weights is going to be 8 plus 8 plus 7 plus 12 plus 9. And if we add all of these up, that gives us a total weight of 44. So this is how we find a tour using the cheapest link algorithm. As you can see, it's very fast and efficient. We only have to find basically one possible option for the cheapest link tour. So this is a very fast and efficient way of solving traveling salesman problems. Thank you for watching, and as always, I'm happy to help with any questions.